This is D. Khalandar Basha, working as Assistant Professor in the Department of ECE. Today I am going to take the topic of a rectifier block diagram and its working principle and analysis of a rectifier. The course outcome for today's topic is apply the PN junction characteristics for the diode applications such as switch, clippers, clampers and rectifiers. So first we will see the definition of a rectifier. A rectifier is a circuit that converts AC voltage of main supply into pulsating DC voltage using one or more PN junction diodes is called a rectifier. AC regulates reverse direction, whereas DC flows in one direction only. Direct current is necessary for the operation of many devices such as laptops, computers, television, and certain power tools. The various rectifiers existing are half-wave rectifier, full-wave rectifier with center tap transformer, full-wave rectifier with bridge circuit, or we can also call it as bridge rectifier. The only one polarity of an alternating current is used to produce a pulsating direct current. The process is called as half-wave rectifier. When both polarities are used, producing a continuous train of pulses, the process is called a full-wave rectification. So first we will study the half-wave rectifier. A half-wave rectifier is the simplest form of the rectifier and requires only one diode for the construction of a half-wave rectifier circuit. A half-wave rectifier circuit consists of the three main components as follows: a diode, a transformer, a resistive load. The block diagram of half-wave rectifier is shown in the diagram. It is consist of various stages. Initially, the input is a AC source which we are giving as the input for the primary windings of the transformer. These transformers are used to lower the input voltage. Usually for DC sources, for rectification, we are going to take for 3 volts, 9 volts, 12 volts like this. So as we are having the input, the supply is 230 volts, that we are lowering by using the transformer section. Next, for rectification, in the half-wave rectifier, we are using a single diode. After rectifying, the output is collected across the load section. The load section is consist of a load resistor R. The input which we are applying for half-wave rectifier is a sinusoidal signal, which is given as V is equivalent to Vm sin omega t, where omega t is taking the values from 0 to 2 pi. So the range of omega t we can write as 0 less than or equivalent to omega t less than or equivalent to 2 pi. Say a single pulse of a sinusoidal signal is consist of positive half cycle as well as a negative half cycle. So the working principle of half-wave rectifier we will discuss with respect to positive half cycle followed by negative half cycle. So during positive half cycle, the voltage or the signal which is exists across the secondary windings is a sinusoidal signal. The shaded area is the input, which is a positive half cycle. During positive half cycle, the node A is positive and node B is negative. So when we are given a positive half cycle for the rectifier circuit, here for the diode D, the P-type material is connected to positive potential. The N-type material is connected to a negative potential through load resistance. Here, the bias on the diode D is forward bias, as P-type is connected to positive potential and N-type is connected to negative potential. The diode is said to be in forward bias. whenever the diode is in forward bias, in the ideal case, we can replace the diode with short circuit. So diode D is forward bias and act as short circuit. So when the diode is short circuit, which is forming a closed loop from the node A to diode resistance and node B again to the transformer to node A, as it is forming a closed loop, we can expect some amount of current which is flowing through the circuit starting from node A, then it will be flows through diode D, then the current will be flows through the load resistance R, then the current will sink at node B. So now, as the voltage whichever you are applying at the secondary windings of the transformer, which is the input for half-wave rectifier, the ideal case we are considering the voltage drop across the diode is 0 volts. So whatever the input which you are applying, the entire input voltage will be appear across the load resistance R. And that current direction, if you see the current direction in the diagram, the current starts well from the positive terminal, that is node A, then it will be flows through the diode D, then it will be flows through a resistance R, and it will sink at node B. And the output, whatever the input which you are applying, the entire input will be depleted across the resistance R, as we are assuming the diode is a ideal diode, where the diode when it is in forward bias, the voltage drop across the diode is 0 volts. So whatever the input voltage which are appearing between the nodes A and B, the entire voltage will be depleted across the resistance R. Now we will move to negative half cycle. So during negative half cycle, the voltage which is present at the secondary windings of the transformer is negative half cycle of the input waveform, so which is shown in the shaded lines. Right. Now here, when we are given a negative half cycle, the node A will be at negative potential and node B will be at positive potential. Now if you see the bias across the diode, as the diode D, the P-type material is connected to negative potential and N-type material is connected to positive potential through the resistance R, the bias on the diode D is reverse bias. In the ideal case, the diode D will act as open circuit whenever it is in reverse bias. So when the diode is in reverse bias, it will act as open circuit. That means the presence of diodes, we can remove the terminals across the diode will be open circuited. So the cross mark I am placing indicating it is a open circuited. So now as the circuit is not forming a closed loop, the amount of current which is drawn by the circuit is equivalent to 0. So as it is creating an open loop circuit, no current will be flow through the circuit. So the output for this negative half cycle we can see as 0 voltage. By combining positive half cycle output as well as negative half cycle output, we can get the voltage, output voltage across the load resistance for a half wave rectifier. So in conclusion, the half wave rectifier working we can conclude as a high AC voltage is applied to the primary side of the step down transformer. The obtained secondary low voltage is applied to the diode. The diode is forward bias during positive half cycle of the AC supply and reverse bias during the negative half cycle. So when the diode is in forward bias, it is forming a closed loop. So whatever the input which are appearing across the secondary windings of the transformer will be exist at the output terminals which we are collecting across the load resistance R. During reverse bias, as the diode is open circuited, no current will be flow through the circuit and the output voltage is equivalent to 0. By combining these two, we can show the output waveform for the half-wave rectifier in the figure. So the input Vn, a multiple cycle we are considering on x-axis omega t and y-axis the voltage Vn. So it is having a period of 0 to 2 pi. In the output, as the forward positive half cycle, it is conducting. So we'll get the output for 0 to pi. During pi to 2 pi, the diode is in reverse bias and no current is flowing through the resistance R, which will causes a voltage drop across the resistance equivalent to 0 during the duration pi to 2 pi. The output voltage is expressed as V is equivalent to Vm sine omega t in the interval 0 to pi. That is 0 less than or equivalent to omega t less than or equivalent to pi. Whereas the V is equivalent to 0 for pi less than or equivalent to omega t less than or equivalent to 2 pi. This is the output voltage expression. V is given as Vm sin omega t, where omega t is taking the values from 0 to pi, and the output voltage V is equivalent to 0 when omega t is taking the values from pi to 2 pi. For analyzing the off-wave rectifier performance, we are going to estimate a few parameters to decide the efficiency of the off-wave rectifier. The following parameters will be explained for the analysis of the off-wave rectifier. They are DC output current or average output current, DC output voltage, RMS current, root mean square current, RMS voltage, that is root mean square voltage, ripple factor, rectifier efficiency, output frequency, peak inverse voltage, peak factor, form factor, and the transformer utilization factor TUF. So first we will see the factor DC output current. Before that, as we know, the current which is flowing through the resistance R, we are seen in the positive half cycle. So the current expression we can write as I is equivalent to Im sin omega t, where 0 less than or equivalent to omega t less than or equivalent to pi, and I is equivalent to 0 for the duration pi less than or equivalent to omega t less than or equivalent to 2 pi. The first factor is average or DC output current. The average current of a periodic function is defined as the area of one cycle of the curve divided by the base. Now in the output voltage, here the output voltage is having the period is 0 to 2 pi, that is omega t is taking the values from 0 to 2 pi, in which 0 to pi the signal is present, that is Im sin omega t if it is current, if it is voltage it is Vm sin omega t. From pi to 2 pi the voltage and current are equivalent to 0. Now we will see the analysis of the DC current or average current. As for the definition, the IDC it is given as, for finding out the area we need to integrate from 0 to t, the time period t, I d omega t divided by the entire duration, that is t. In the off-wave rectifier case, here the time period t is 2 pi. So by substituting t is equivalent to 2 pi and I value from 0 to pi as Im sin omega t, whereas from pi to 2 pi the value of the current is equivalent to 0. By substituting this, we can get IDC current as follows. So IDC is equivalent to 1 by t integral 0 to t I d omega t. As we know, t is equivalent to 2 pi. So substituting this, we can write the expression as IDC is equivalent to 1 by 2 pi integral 0 to 2 pi I d omega t. In the off-wave rectifier output, the signal is not a uniform signal which is having the expression from 0 to 2 pi. So we need to split the integral from 0 to 2 pi as two integrals, that is from 0 to pi plus pi to 2 pi. Then we can write as IDC is equivalent to 1 by 2 pi integral 0 to pi I d omega t plus integral pi to 2 pi I d omega t in the duration of pi to 2 pi as current is equivalent to 0, substituting the value as 0. So we can get the expression as IDC is equivalent to 1 by 2 pi integral 0 to pi ID omega t plus integral pi to 2 pi 0 into d omega t. So substituting the expression for I in the duration 0 to pi, then we'll get IDC is equivalent to 1 by 2 pi integral 0 to 2 pi. In this integral 0 to pi time, the current expression is given as I is equivalent to Im sin omega t. Substituting this, so integral 0 to pi Im sin omega t into d omega t. However, the current from pi to 2 pi is equivalent to 0. Substituting as 0 in this duration, you'll get plus integral pi to 2 pi 0 into d omega t. See here, the integral of Im is a constant, so Im you can take as outside. The integral of sine, it is given as cos omega t. So IDC is given as 1 by 2 pi minus cos omega t. Boundaries are 0 to pi. However, from pi to 2 pi, the value of the integral is 0. So which is given as Im by 2 pi. Substituting the upper limit minus lower limit, then we can write as minus of cos pi minus cos 0 by substituting the upper integral as well as the lower integral. What is the cos pi value? Here it is minus 1. So substituting cos pi values and cos 0 values, then we can write IDC is equivalent to Im by 2 pi minus of cos pi is minus 1 minus cos 0 is 1. It will reduce us to Im by 2 pi minus 1 in the inner portion, minus 1 will get as minus 2 into minus will get as plus 2. So which will reduce us to Im by 2 pi into 2. Here 2 get cancelled. Then the IDC or I average, it is given as Im by pi for half wave rectifier. Now in the circuit of the half wave rectifier, here the voltage which is present at the secondary windings is Vm. The current which is flowing through the circuit is Im. If the internal resistance of the diode, if I consider as Rf, then Im expression we can write as Im is equivalent to Vm divided by Rf plus R. If you are considering the secondary windings, Rs resistance also we can include. I am assuming the resistance of the secondary winding Rs is equivalent to 0. So Im, I can relate with the Vm as Im is equivalent to Vm divided by Rf plus R, substituting in IDC expression, which will lead to Vm divided by pi into Rf plus Rm. The resistance of the diode, which is Rf, is always much less than the load resistance. So we can neglect Rf plus RL, we can reduce to RL also. So this I can write as approximately Vm by pi into RL. Since Rf is much less than RL. This is the first parameter. The second parameter is average or DC output voltage. The average or DC output voltage, VDC, it is given as IDC into RL. The voltage which we are considering across the output resistance, that we are considering as RL, the current which is flowing through that resistance is IDC. So then VDC is given as IDC into RL. In the earlier, we are derived the expression for IDC as Im by pi or Vm by pi into Rf plus RL. Substituting the value of IDC, you will get VDC is equivalent to Vm divided by pi into Rf plus RL into RL. As we know, the resistance of the diode, that is Rf, is much less than RL. So then we can write Rf plus RL. Rf plus RL is approximately equivalent to RL. Then we will get VDC is equivalent to Vm by pi RL divided by RL. RL get cancelled. So left out the factor is Vm by pi, that is the average or DC output voltage. The third factor is RMS current. The expression for RMS current, it is given as square root of 1 by t integral 0 to t I square d omega t. Root mean square. Root t factor is mean. This is the squared signal. So that's why it is called as RMS. Root mean square. By substituting t is equivalent to 2 pi, then we can rewrite IRMS expression as square root of 1 by 2 pi integral 0 to 2 pi I square d omega t. For half-wave rectifier, the output signal, that is current, output current is not having the same expression for 0 to 2 pi. So we are going to split the integral from 0 to 2 pi as it is the sum of two integrals, that is 0 to pi plus pi to pi. By splitting the integral, then we can rewrite the IRMS expression as 1 by 2 pi 0 to pi. In the duration 0 to pi, the current expression is Im sin omega t, as it is I square. So Im sin omega t whole square into d omega t plus integral pi to 2 pi. In this duration pi to 2 pi, the current is 0. So 0 square into d omega t. By substituting sin square omega t in terms of cos 2 omega t, as we know, cos 2 omega t is equivalent to 1 minus 2 sin square omega t. From this, the sin square omega t we can derive as 1 minus cos 2 omega t divided by 2. So in place of sin square omega t, we can substitute as 1 minus cos 2 omega t divided by 2. The Im is a constant, so this Im factor we can take outside. So then it will give us as Im square by 2 pi integral 0 to pi. In place of sin square omega t, we can write as 1 minus cos 2 omega t divided by 2 into d omega t. Now we need to integrate the term 1 minus cos 2 omega t divided by 2 with respect to omega t, where omega t is ranging from 0 to pi. So that will give us the 2 as a constant. So I am taking outside. So then we will get Im square by 4 pi integral 0 to pi 1 minus cos 2 omega t into d omega t. Splitting this integral, we can write IRMS is equivalent to 1 Im square by 4 pi integral 0 to pi into 1 into d omega t is given as omega t minus cos 2 omega t integral is minus sin 2 omega t divided by 2. The lower limit is 0 and the upper limit is pi. Substituting upper boundary and lower boundary, the IRMS we can rewrite as Im square by 4 pi. In place of omega t, we can write pi minus 0. So that is pi minus 0 minus substituting omega t is equivalent to pi. Then you will get sin 2 pi minus sin 0. As sin 2 pi is equivalent to 0 and sin 0 is equivalent to 0, the term sin 2 pi minus sin 0 will be vanishes. Then IRMS it is given as square root of Im square by 4 pi into pi. Here pi get cancelled. Left out is square root of Im square by 4, which will give us Im by 2. Im by 2 is the IRMS current for half-wave rectifier. As we know, Im and Vm we can relate as Im is equivalent to Vm divided by Rf plus RL. So IRMS expression in terms of current we can write as Im by 2. In terms of voltage we can write as Vm by 2 into Rf plus R. The next factor is RMS voltage. The RMS voltage it is given as Vrms is equivalent to IRMS into Rm. We are estimating the RMS voltage across the load resistance. In the earlier slide, we got IRMS expression. Substituting this VRMS, it is given as VM by 2 into RF plus RL into RL. As we know, RF is much less than RL. VRMS is reduced to VRMS is equivalent to VM divided by 2. RF plus RL we can write as RL into RL. RL get cancelled. Then you'll get VRMS is equivalent to VM by 2. The next important factor for rectifiers is ripple factor. It is defined as the ratio of RMS value of AC component to the DC component in the output is known as ripple factor. As we know, according to the definition of rectifier, it is going to convert the AC input into pulsating DC. So what is by pulsating DC means ripples are AC components superimposed onto the DC components. That means across the load resistance RL, we are going to have both the components, IAC components as well as IDC components. The objective of rectifier is for converting AC to DC. So most of the components should be DC and less components should be AC. Now we will see the ripple factor for of a rectifier. It is given as the expression ripple factor is equivalent to RMS value of AC component divided by DC value of the component. Here I am considering the component as current component. So the ripple factor it is given as IRRMS divided by IDC. Here the IRRMS, IDC and IAC are related as IRRMS is equivalent to square root of IRMS square minus IDC square. As we know, the IRMS square is equivalent to IRRMS square plus IDC square. So from this IRRMS expression is given as square root of IRMS square minus IDC square. Substituting the IRRMS term in a ripple factor expression, then the ripple factor expression we can express as IRRMS as IRMS square minus IDC square divided by IDC. When you send this one into the square root, it is becoming IDC square. So IRMS by IDC whole square minus IDC by IDC is equivalent to 1. So the ripple factor it is given as square root of IRMS by IDC whole square minus 1. Substituting IRMS and IDC component in the ripple factor, then we can write the ripple factor as IRMS is equivalent to IM by 2 for half-wave rectifier and IDC is equivalent to IM by pi for half-wave rectifier. Substituting these two components in the ripple factor, then the ripple factor expression we can write as square root of IM by 2 divided by IM by pi whole square minus 1. Here IM get cancelled. Then the ripple factor we can write as pi by 2 whole square minus 1. By evaluating the expression pi by 2 whole square minus 1 under square root, then we will get the ripple factor is equivalent to 1.21. Here for half-wave rectifier, the ripple factor is 1.21. Here the measure ripple factor, what it is going to convey is the ripple factor is given as 1.21, that we can write as 121 divided by 100. What is the expression for ripple factor? It is IAC divided by IDC, or we can also express as IRRMS divided by IDC. So in the output component, current component, 121 parts are ripples, 100 components are DC components. So half-wave rectifier, as it is producing more ripples at the output side, the rectification of half-wave rectifier we can consider as it is poor rectifier. For a good rectifier, always the ripple factor should be less. The ideal value of the ripple factor is 0. The next parameter for rectifier analysis is rectifier efficiency. It is the ratio of DC output delivered to the load to the AC input power. It signifies how efficiently the rectified circuits converts AC power into DC power. The efficiency it is given as output power divided by input power for percentage calculation multiplying with 100. Here the output power we are going to consider as PDC, that is DC power. Input power is PAC, that is AC power. The efficiency we can rewrite as the DC power divided by AC power into 100. The PDC here it is given as IDC square into RL. For half-wave rectifier, IDC is equivalent to IM by pi. Substituting this, PDC will get as IM square divided by pi square into RL. Whereas PAC it is given as IRMS square into RF plus RF, because AC component is circulating across the diode as well as the load resistance. So the PDC is given as IM square by 4 into RF plus RF. Substituting PDC component and PAC component in the rectifier efficiency expression, then efficiency we can write as IM square by pi square into RL divided by IM square by 4 into RF plus RL into 100. Here IM square get cancelled, which will reduce us to 4 by pi square into RL divided by RF plus RL into 100. As we know, RF is much less than RL. Substituting this, RF plus RL approximately equivalent to RL component get cancelled. So then we will get efficiency is equivalent to 4 by pi square into 100, which will give us 40.56. So the ripple factor rectifier efficiency for half-wave rectifier is 40.6, which indicates out of 100 units of AC power, 40.6 units of power is converted into DC. The remaining power is wasted. The next parameter is output frequency. The signal for the input is shown in the top, which is having a time period of 0 to 2 pi. This I am considering as the input time period Ti. So the input frequency Fi it is given as 1 by Ti, which is equivalent to 1 by 2 pi. For half-wave rectifier, the output frequency calculating will be done first by measuring the time period of the output signal, which is T0. Here the T0 is also equivalent to 2 pi. So the output frequency F0 is equivalent to 1 by T0, where T0 is equivalent to 2 pi. As Fi is equivalent to 1 by 2 pi, F0 is also equivalent to 1 by 2 pi. So for a half-wave rectifier, the output frequency is equivalent to input frequency. The next parameter for rectifier analysis is peak inverse voltage. It is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. The peak inverse voltage across the diode is the peak of the negative off cycle for a half-wave rectifier. So we will see during negative off cycle, that is node A is negative, node A is positive. Here we are going to have the maximum voltage is equivalent to Vm. As it is a negative off cycle, the diode is open circuited. So across these two terminals where the diode is placed, if we see the circuit from these two terminals, whatever the voltage drop inside it is present, that will give the peak inverse voltage. When the diode is open circuited, here the amount of current which is flowing through the circuit is 0. So what is the voltage drop across the resistance R? It is equivalent to a 0. So now the peak inverse voltage for half-wave rectifier, it is given as maximum voltage is Vm plus what is the voltage drop across resistance R? 0. So that will give us the peak inverse voltage for half-wave rectifier is Vm. The next factor is peak factor. The peak factor is defined as the ratio of the maximum value of RMS value of an alternating quantity. The peak factor, it is given as peak value divided by RMS value. What is the peak value? For current component, we can take as Im. RMS value for half-wave rectifier is Im by 2. So here Im get cancelled. So the peak factor, it is given as 2. The next parameter we will see is form factor. The form factor is defined as the ratio of RMS value to the average value of alternating quantity. So the form factor, it is given as RMS value divided by average value. For half-wave rectifier, the RMS, it is given as Im by 2, whereas the average value, it is given as Im by pi. Here Im get cancelled. So the form factor, it is given as pi by 2, which is equivalent to 1.57. The last factor for half-wave rectifier analysis is transformer utilization factor, TUF. In the design of any power supply, the rating of the transformer should be determined. This can be done with the knowledge of the DC power delivered to the load and the type of the rectifier circuit in use. The transformer utilization factor TUF, it is given as DC power delivered to the load divided by AC rating of the transformer secondary. The TUF, it is given as DC power delivered to the load, we can take as PDC divided by, for transformer rating, PAC rated. The PDC expression is IDC square into RL, whereas PAC rated, it is given as VRMS divided by RMS. The PAC rated, the VRMS is calculated with respect to the input voltage but not with respect to the output voltage. By substituting IDC expression, VRMS expression, IRMS expression in the TUF, here what is IDC expression for half-wave rectifier? The IDC is given as Im by pi. The VRMS for the input voltage, it is given as Vm by root 2. The IRMS for half-wave rectifier, it is given as Im by 2. So this is with respect to the input signal. This you need to remember. By substituting IDC, VRMS and IRMS in the TUF, the transformer utilization factor we can rewrite as IDC square, that we can write as Im by pi whole square into RL, divided by VRMS is Vm by root 2, IRMS is Im by 2. Here Im square, this we can write as Im square into RL divided by pi square whole divided by Vm into Im divided by 2 root 2. Here Im get cancelled. We know that Vm is equivalent to Im into Rf plus RL, as since Rf is much less than RL, then we can write Vm is equivalent to Im into RL. So in the numerator we are having the component Im into RL, in the denominator we are having Vm. So Vm, Im, RL get cancelled. So the left out is TUF, it is given as 2 root 2 divided by pi square. By finding out this value, we will get TUF is equivalent to 0.2867 In percentage, we can write this one as, by multiplying with 100, we'll get 28.687 percentage. This we can approximate as 28.7 percentage. Otherwise, in terms of decimals, we can write as this is 0.287. This is the transformer utilization factor TUF for half-wave rectifier, which is 0.287. So with this, I conclude the half-wave rectifier working principle and the analysis. The various points which were discussed in this class is, what is a rectifier? So the rectifier is defined as, it is a electronic circuit which is used to convert the alternating current into pulsating DC. The pulsating DC means the AC ripples superimposed onto the DC component. The objective of the rectifier is, for many peripherals or electronic gadgets, we require a DC source. So from the AC source which we are getting for households, that we need to convert into DC source. For that purpose, we are using rectifiers. So the various rectifiers existing are half-wave rectifier, full-wave rectifier with a transformer, center-tap transformer, full-wave rectifier with bridge circuit. Under these rectifiers, we have studied half-wave rectifier, which is a consist of a transformer, a diode, and resistance. The half-wave rectifier will conduct in positive half cycle and it will not conduct in negative half cycle. That means it is rectifying only positive half cycle of the input. The negative half cycle, the output is producing to a zero. After getting the output waveforms and deriving the expressions for output current as I is equivalent to Im sin omega t, where omega t is taking the values from 0 to pi, and I is equivalent to 0 when omega t is taking the values from pi to 2 pi. For finding out the analysis of the half-wave rectifier, we have derived the expressions for DC current or average current, DC voltage, RMS current, RMS voltage, ripple factor, rectifier efficiency, output frequency, peak inverse voltage, form factor, peak factor, and transformer utilization factor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.